My name is Yo, and Ben both of us will be co-hosting this workshop. We work for the UCLA Institute for Digital Research and Education. Today's agenda, let me just get right to it, will be to introduce data science with Python. Ben will be the host for this, and we're going to cover a wide range of libraries that are listed here. So this is going to be mostly day one, which is kind of setting the foundations of data science and introducing you to a variety of popular Python libraries and looking at an iris data set that Ben will be taking you through. Day two, which is tomorrow at the same time, we'll be taking you through a case study. So we'll be looking at a data science project, looking at LA arrest data, and doing some cool data viz stuff with 3D mapping. And these are the libraries that we'll be looking at for that. And Ben will also do some kind of advanced data science techniques with machine learning using PyTorch and TensorFlow. So that's the agenda for our two-day workshop. And once again, welcome everybody. And I'm now going to hand it over to Ben. And I'll stop my share.
Thanks, Joe. And welcome everybody. It's nice to see that we have so many interested people. Let me share my screen here. So do you see the slides?
Yep, all good.
Yep, okay, thank you. I turned off my video here too, just so that just in the interest of preserving some of my internet bandwidth, since we'll be working through a lot of interactive exercises today. And I want my voice and my computer screen to come through without too many glitches. So I've turned off my video. Yo set us up very well. So I just have a few introductory remarks about data science, just to lay the groundwork. I'm sure if you're coming to this workshop, you probably have some impression of what data science is. It's a very hot topic right now. And generally speaking, data science is about drawing useful conclusions from data sets through exploration, prediction, and inference. So I got this definition from the Data 8 course that's offered at Berkeley. As you can see from this particular definition, data science isn't necessarily a new topic. It's drawing conclusions and exploring data have been around for a very long time. It's kind of coming to the forefront because we're capable now of capturing and analyzing huge amounts of data. This topic is very interdisciplinary. If you would look at the different departments that all of you are drawn from, it really spans the entire campus at UCLA. And basically, any discipline where you have data that you can gather and try and analyze is really affected or can be influenced by applying data science principles. And data science draws on a wide range of skill sets as well. So skill sets for mathematics, statistics, computer science, information science, and domain knowledge, where domain knowledge is simply the expertise in the particular field where you're gathering the data. And this here, of course, is what brings a lot of different departments here to this particular workshop. The basic process can be thought of conceptually rather simply. So at the beginning, you simply ask an interesting question, or usually you might have some data that you're looking at and you want to try and analyze the data and see if the data tells you anything interesting. This is where the process usually starts. So we're talking specifically in this workshop about Python. Python and computer science won't tell you anything about how to ask an interesting question. That's rather obvious, but it's worth stating because really to use data science effectively, you have to be able to ask intelligent and informed questions. To some extent, you can get an idea of what questions you want to ask from simply looking at the data. So one of the most important and often time-consuming processes in the data science pipeline here is how do you get the data? And kind of relevant to this is you have to know how the data were sampled. You have to have some sense for what data is relevant and what data is not. And you have to be, in certain situations, you have to know whether there are concerns about the data. So in particular, in today's climate, data is a very, it's an asset. So it's, you can charge money to access data sets. There are very large data sets, and in different fields, there are privacy issues connected with the data, particularly if it's connected to identifying information about people involved in the data set. Once you get the data and you're sure that it's kind of in a clean state and in a format where you can easily analyze it, then you start exploring the data. So today's workshop will be mainly about getting the data and exploring the data. And exploring the data can be one of the most fun parts of data science. This is where you come up with very cool graphics. There are a lot of libraries out there to plot the data. You can use these visualizations to inform your understanding of the data, as well as to inform the previous step of getting the data. When you plot the data, it's a little easier to try and infer whether there are anomalies or patterns in the data. Once you've explored the data, the next step is to model it or to draw conclusions about it. So another hot topic is machine learning. And we'll be talking a little bit about this tomorrow. Machine learning is one way to try and model the data and to try and make predictions about new data that you might be gathering in the future, or say you want to predict some kind of behavior. You can use your current existing set of data to try and inform predictions about how the data might be in the future. Along with modeling data, I would also include simply analyzing and drawing conclusions from the data. So in some cases, you don't necessarily want to predict anything from the data, but you do want to make conclusions about it. And you want to make sure that your conclusions are supported by the data that you have, and you want to quantify the uncertainty that you have in making those conclusions. So the data science process itself is really about how to make informed conclusions from the data that you have. And then finally, at the end, we have communicating and visualizing the results. So often this data science process isn't just for our own personal satisfaction, it's to come up with conclusions that you can share with other people. So in sharing those with other people, there are kind of a growing set of techniques for communicating and visualizing the results and for effectively communicating them with other people. This is a Venn diagram that kind of just reinforces the different sets of knowledge that are brought to bear on the data science process. The hacking skills are things like computer coding skills. There's the math and statistic knowledge, which is required, say, for making models and for quantifying your uncertainty. Substantive expertise is where the domain knowledge comes to play. This is one of the first Venn diagrams that was made when data science was kind of becoming an established field. And there are quite a range of Venn diagrams which have been generated since. But this one is kind of a slightly more evolved one, which gives you a flavor of the different concerns for each of these areas. So with substantive expertise, this is where you really come and you ask questions of the data. In business scenarios, you might try and understand your customers or how to predict customer behavior. You want to know how to define the metrics that matter so that you know which conclusions it is that you're trying to establish. Substantive expertise, we won't be talking at all about today. This is very particular to whatever field that you're applying data science to. And in particular, Python won't have anything to say about informing your substantive expertise. Python really falls into the hacking and coding part, but hacking and coding is quite a large domain in itself. So this is where concerns come about data governance. SQL is mentioned here, but this is more just the wide variety of formats that you have for storing data, how you might prepare data to analyze it, how you can get the right data. And then the math and statistics, this we won't be talking about so much either, although to some extent we'll be talking about machine learning models which are involved in model fitting. But really a lot of advanced mathematics can be applied to data sets and to try and draw conclusions from data sets. So machine learning falls kind of in the intermediate region between the computer skills and the math and statistics. Data science falls squarely in the middle where you have to have some domain expertise, but some computer experience as well as the math. Traditional research, which isn't computationally heavy, tends to fall between the domain knowledge and the math and statistics. And then engineering the data to try and get it into a state where you can make substantive conclusions from it falls between the coding and the expertise. So that's the extent of my setup. This workshop, our emphasis is very much on with Python. So this is intended to be a very applied introduction. And the hope is that by exposing you to the different Python tools and by walking you through some very specific things that you can do with Python, the idea is that you will first gain some skills that you can readily translate into your own projects. I know there are a lot of you here who don't necessarily have a whole lot of programming experience, but the examples we'll walk through will hopefully help you get to a better state of being able to use Python for any data science activities you want. And the second goal is just to give you exposure to the concepts and tools that data science work with in this very applied setting. Okay, so we're going to jump right in. And you'll mention that we'll be interacting with Jupyter notebooks. For those of you who would like to interact with the materials, I would like you to go to this particular website. I'll copy it into the chat. On this particular page, this is a GitHub repository that I've made available with the materials that we'll be working with today. When you get to the website, you'll see a variety of files, but if you scroll down, there are links here that will take you to the sites that you can interact with through your web browser, which will allow you to execute the programming commands that I'll be talking about. For those of you who are affiliated with UCLA, I would recommend clicking on the first one, the Launch into Jupyter Hub. This is a Jupyter Hub that we host at UCLA. For those of you who aren't able to do the UCLA authentication, you can click on the Launch Binder link here, and that will launch you into a similar environment to what I'll be showing. So when I click on this one, you'll see a blue scrolling bar. You might see a blue scrolling bar after you first log in. The blue scrolling bar will just tell you that it's setting up your environment. And then you'll see another blue scrolling bar when it's essentially cloning the files into your local directory on this Jupyter hub. And then you should land in a directory which looks like this. So for using the IDRI, there's a question about the pros and cons of using the IDRI Jupyter Hub versus Google Colab. In this particular one, I've installed all of the packages that we'll be working with. So you won't necessarily be able to use the Google Colab environment at the moment unless you're also willing to install the packages. That's the main pro and con for right now. We can talk about different pros and cons at the end if you're interested. I'm gonna So the first one that we want to interact with, well, so there's one note before we start. I've included notebooks that have a suffix of both starter and finished. If you don't feel like typing in all of the commands that I'll be talking about, I would recommend opening up the one that says finished. The one that says finished already has all of the commands written into the cells. The one with starter is for those of you who actually want to work through the examples as I'm talking about them. And that's what I'll be opening up myself. I think that's the essential information. For those of you who haven't interacted with Jupyter before, the way to open a file is simply to click on the file name, and that will open a different tab in your browser. So for example, the first one will be interacting with the 01 getting data and Pandas starter. So when I click on that file name, it opens up a new tab, and it opens up this Jupyter notebook. As a bit of background, you don't have to know a lot about interacting with Jupyter notebooks to run these, but you do have to know how to run a cell. To run a cell, which is what's bounded here by this highlight box, you click Shift and Enter, and that will run the cell. If it's a cell like this, you won't see any evidence that it's been executed. It's simply text or other multimedia that's in the cell. You can also run a cell by coming up to the top and clicking on the Run button. That will also run the cell. So for the question in the chat about there's nothing under your tree, you have to import the files by clicking on that link in the GitHub repository. That's the way to clone the files into your local environment on the Jupyter Hub. All right, so I think this is now the basic setup. Does anybody need more time to get set up before we start? So for the two people in the chat who are having trouble on how to get there, were you able to make it to the GitHub repository okay? So I'm looking at a couple of you. Yes, so there are some new nodes that are still starting up on the hub. I checked the status of those. It may take just a couple more minutes here for, since there are a lot of you logging in, it might take a couple minutes before all of you are fully logged in the environment to set up for all of you. As long as the blue bar that's scrolling across the screen doesn't turn red, it's still in the process of starting. If it turns red and errors out, then I would suggest just trying to refresh your browser window. For those of you who are being asked to authenticate that are already on the VPN, you will have to actually do the UCL authentication in order to get logged into this service. For those of you who asked if there will be a way to get back to the one which has all of the commands written, all of the files should be cloned there and saved in this. Let me go back and show you the GitHub repository. So in this GitHub repository are the files that are saved. You can always access the one that has the built-in commands by opening the one that says finished. There's a finished one for the first, the second, and the third notebooks that we'll be working through. For those of you who don't want to wait around for your node to start up on the IDRI Jupyter Hub, I would recommend coming back to this GitHub page and clicking on the launch binder link. For the person who's failed to get a username from CI logon, I would recommend to come back here and click on the launch binder link. So the Jupyter Hub requires that just knowledge about what your email is at UCLA. And if that information hasn't been publicly released by UCLA, then the Jupyter Hub won't know how to identify you with a user account. So in that case, it's best to go to this launch binder link. All right, so I think for those of you who are trying to log into the Jupyter Hub, it looks like the nodes have been started and containers are running for all of you. Let's see, so for the person who says there's nothing in my tree on Jupyter Hub, are you logged in successfully? Do you just, so I'll type for it here in the chat window a little bit. All right, I think once we, sorry for the delay here, but I think once we get set up, we'll be all good. All right, I'm going to start moving on. I think if you'd like to communicate with Yo in the chat window, he can help you get up for any of those of you who are still having trouble. All right, so we'll be opening this one called 01 Getting Data in Pandas. I'll be working with the starter one, or you can work with the one that says finished, which has the commands. So as Yo mentioned, I'll be talking specifically about the iris dataset. This dataset was used by Fisher at the beginning of the 20th century. Fisher was is a very famous statistician, and he looked at linear discriminant analysis in his paper. So his data set is one of the most common used probably examples when you're first learning machine learning. The data set isn't very complicated. It looks at the sepal length, sepal width, petal length, and petal width of 3 different species of iris. There's Iris setosa, Iris versicolor, and Iris virginica. For each flower, he looked at 50 different flowers, and he made measurements of these 4 parameters for each of the 50 flowers for each different species. So there are a couple reasons that this is used commonly in machine learning, and we'll kind of come across the interesting features of this when we start exploring the data. For the moment, I'll just leave it at this as the introduction. This is a snapshot from his actual paper, and you can actually look at the reference here if you're interested in looking at the paper. So we're going to work through a hypothetical example. So say that somebody has entered data into an Excel spreadsheet for us to analyze. For those of you who are coming at Python for the first time, you know, this might be a relatable thing for somebody to share an Excel spreadsheet of data with you. For those of you who are more familiar with Python, it might be kind of interesting to note that Python has a library for importing Excel data. So the first library we're going to work with is openpyxl, which is a Python library to read and write Excel 2010 Excel spreadsheet data. So in Python, the way to import a library is just to type open or import and then the name of the library. So I'm going to say import openpyxl, and I type shift and enter, and that will execute the cell. You can tell it's executed because the 1 pops up in the brackets here. That tells us that the library has been imported. And then the highlighting of the cell advances to the next cell. So we imported the library, and now we have to use this library to import the data that we have. Let me hide my video panel here. All right. So I've shared this data with you in the data folder that you have in your files. You don't have to go to it yourself, but I'm just going to show you inside of this data folder, there are a variety of files that we're going to be interacting with. The first one we'll interact with is its Excel spreadsheet file, which is the XLSX. So to import the data, I'm going to assign it to a variable, just WFB for, say, workbook. I'm going to type the name of the library, which is openpyxl, and then the name of the function to load in the data is, load workbook. And then the 2 parentheses tell us that we're going to enter in now the parameters for the function. The only parameter that we have to enter in is the name of the file. So here, the name of the file is, it's in the data folder. So data /irish-excel-start and then .xlsx. Interesting.
It's star there, not start.
I'm sorry? Oh. Starter, thank you. Yes, so that successfully, that loads this into this particular variable. To look at the variable that's been loaded, sheet names will give us the names of all of the sheets that are in the particular Excel spreadsheet that we've opened. So typing wb.sheetnames, this is an attribute of the wb variable, tells us that there's one spreadsheet in the file that we've opened, and it's called iris-comma. We can access the data that's inside of it. I'm going to assign the workbook to a particular variable. So in this one, WB is the file handle that we've opened, and then brackets, and then the name of the worksheet in quotes. And then I assign this to a variable named sheet. So this is a bit of setup. In order to look at the data, which is kind of what we want to do in the first place, we have to iterate over sheet. And for the moment, I'm just going to print out what the values in it are. So to do a loop, a for loop in Python, you say for and then the iterating variable I, and what it is that I want to iterate over, which is sheet, and I want to iterate over the values in the sheet. And then I put a colon. And I just want to print the values. So I say print parentheses I. And this will print out the variables finally, the data measurements from the Excel spreadsheet that I've imported. So this is the basic process of loading data from an Excel spreadsheet. First, I import the library. I load the workbook that's associated with a particular file, Excel spreadsheet file. Then I identify the spreadsheets that are inside of that file. And for a particular one of them, I can access the values by coming here and saying sheet.values. That will get me a list of the values. And then I'm printing them out here. These are Python tuples. They're inside of parentheses and they're separated by comments. So the first tuple that we see here tells us the headers for our data. There's the species and then the 4 different parameters that are measured in this iris data set: petal length, petal width, sepal length, and sepal width. You can scroll down through this window if you want, but you can see there's a species for Setosa, there's one for versicolor, and there's one for Virginica. For the question, why is it I? This I can actually be anything. So it's just a random variable, as is mentioned in the comments there. If you just want to get a list of the values, so sheet.values will tell you what this object is. And when this is output, for those of you don't have to worry about what this means. This is kind of Python jargon for what this particular object is. But you can see when we just type sheet.values, it isn't actually showing us what the values are inside of this notebook. We can get the values by converting them into a list. And we can convert them into a list by saying list parentheses and then the sheet.values that we want to be converted into the list. So when I execute that, the list you can see is what's included in the brackets. So each element inside of the brackets is a tuple, 1 tuple per row, and then each row is, all of the rows are included in the starting bracket and the ending bracket. And I don't just want to print this out. I actually want to use the data. So I'm going to assign the data to a variable. I'm going to say wlist is equal to this list that we've generated. And when I execute that cell, it doesn't print out anything because all I've done is I've assigned it to a variable. So the variable now is what has the list. If we enter WB list in a new cell and execute it, it will show me the list that's inside of this variable. So Python in this Jupyter notebook will know that if I just enter the variable name, it will print out, if it can, what's inside of that variable. And now since it's in a list, I can index the list. So for example, if I type WB list bracket 0 end bracket, that will give me the first element in the list. If Python is 0 indexed, the indexing starts at 0. And this gives me the first element of the list, which is the headers for our data columns. The rest of the data is stored in the subsequent items in the list. So if I copy this down, I want everything from the element 1, which is our second row, up to the end. A shortcut for doing that is to say 1, the indexing is going to start at 1, and then colon, and then just leave what's after the colon blank. And that means to go to the end of the list. So when I execute that, that doesn't show me WB list 0 because I'm starting at 1, but it includes all of the different rows now for the rest of the data. So now we have the headers for our data set. And we have all of the data inside of these tuples, and all of the data is inside of this list. What we want to do now, what I'm going to introduce now is a different library called Pandas, which is probably one of the most widely used tools in Python for interacting with these data, for manipulating and analyzing data. Pandas comes from a panel data analysis, and it's widely used for data munging because you can, it has a very nice way of structuring and manipulating the data to present it in nice formats. You'll see compared to what we did here, it has a wide variety of methods for actually conveniently importing data. It can actually work with Excel data files, as well as a wide variety of additional file formats. And it has a lot of convenient functions for quickly plotting data. So we're going to turn what we just used into a data structure that Pandas can use.
Hey, Ben, maybe you can
Yeah.
pause for a second and let people catch up.
Sure. So for the people who are having trouble, don't start with the starter notebook. Go directly to the finished one. I'm going to open up the finished one here myself, just to show you what it looks like. When you open up the finished notebook, you'll see exactly what it is that I've been typing in. And actually, just go up to the top, click on cell, and click on run all. When you click on run all, it will execute every single cell that's in the notebook. There's one cell that it's going to hang up on because that's something that I've intentionally asked it to hang up on. But after that one, come down to the next one and click on run all again. And it, we'll get to this later. But at the beginning, what you want to do is just to run all of them so that all of the output is generated. And then when the output is generated, just follow along with the directions that I'm talking about and don't worry about actually entering in the code. As far as some of the terminology, yes, it looks like some people are filling in the questions to the, filling in answers to the questions that are being asked in the chat. So I do realize there's quite a wide variety of different skill sets here. One of which is people who don't have any experience at all in Python. So the as far as what WB list 1 colon is, you can access any element in a list. Let me start here and just enter in a list. 1, 2, 3. This is a Python list. So a Python list is included, is just a list of elements between brackets. You can index, you can get specific elements in this list by using an index. So A with 0 in the brackets means that I'm accessing the first element in this list. I can access all of the elements in the list by putting in a colon. So the colon just means that I haven't specified what the first and the last element are. If I do from 0 to 3, that gets me all 3. If I do from 0 to 1, that only gets me from the 0 and then it stops at the first. So it doesn't return the first, it just includes the 0th one. And if I don't include the end one, it means that I'm not specifying what the ending parameter is, and it just assumes that I want to go all the way to the end. So coming up here, WB list 1 colon just means that I start, essentially I start at the second row because Python is 0 indexed. The 0 element in this list is this first tuple, which is, a tuple is different from a list because, as was mentioned in the questions, it's immutable, but it still essentially acts like a list. And then going from 1 to the end does accesses the second row all the way to the end. As far as modules and pandas, when I say import, so here I'm going to be working with pandas. Pandas is a Python library, and a library consists of a set of functions that you can execute. In order to inform Python that you actually want to use the library, the first thing you have to do is tell Python that you want to use the functions. And you tell it that by using this import command. So import is our way of telling Python that we want to use the library, and then we say the name of the library. And in this particular case, the common convention is to give it a different alias. So rather than typing pandas out all the time, it's very commonly done to alias it as PD. Import pandas imports all of the functionality of pandas. And then anytime we want to use pandas, we're going to use this PD abbreviation. And then I execute that with shift and enter. That imports the library. The imports can happen at any point, although usually you want to, just in the interest of sanity for your Python programs, you want to import them all at the beginning so that you keep a better flow of what it is in your Python program. In this particular case, I'm importing them at different parts just because I'm introducing different libraries at different times, and I don't want to import everything at the beginning. So now we've imported pandas as PD, and for the moment, I think it's best in the interest of explaining things to come down a little bit longer to this place that says pandas can help us explore and clean the data. So I'm going to take this time to explain what these libraries are. Pandas, Python is the programming language, but pandas, NumPy, and SciPy are all Python packages, and there's, not to be more confusing, but there's the SciPy ecosystem, which has the same name as the SciPy library. But the tools that you use for scientific computing in Python typically involve these fundamental libraries. Python is the general purpose programming language. NumPy is a package that has a lot of functions for doing numerical computations. If you work more with Python, you'll definitely come across NumPy. At a very high level, the importance of NumPy is that it defines numerical array and matrix types. And it allows you to do computations on these arrays and matrices very efficiently, very fast. SciPy is a related library. So with SciPy, you get more numerical algorithms, including signal processing, optimization, statistics, and etc. And then Matplotlib, which we'll be talking about, is a Python package which gives you functions for generating graphics. So with Matplotlib functions, you can generate 2D plots. You can also generate 3D plots. And then Pandas is kind of built on top of this ecosystem. So Pandas functions call these underlying functions. And the reason we use Pandas is because it offers functions that allow you to manipulate data. And it's built on top of this NumPy library, which makes available access to numerical array and matrix types and allows you to manipulate them very fast. So I'll come back up here in just a bit, but to show you what functionality you have in NumPy and in Pandas. I'm going to go down to this cell underneath series and data frames. NumPy is another name of a Python package, so we can import it and make its functions accessible by saying import NumPy. And then we give it an alias. We say we import it as NP. So I'm going to execute that with shift and return. For the next one, PD is our alias for Pandas. And Pandas has a function called series. In Pandas, there are two basic data types to keep track of. One is series, which is like a list for Pandas, and one is a data frame. A data frame is like a table. And you'll see this when I execute these two cells. So I'm going to execute these two cells just to generate the output. Including S on its own line here just prints what S is. So with S is the Pandas series. S is called a series, but it has an index that's associated with it. This first column is the index of this object. And then what's next to the index are the values that we've assigned to this particular series. So we specified the series here inside of the parentheses. This is just a regular Python list because it's in between brackets. And then we have the elements of the list. np.nan is a way to specify not a number from the NumPy library. So this is something that's calling from the NumPy library. It's getting NumPy's representation of a NaN value. So in essence, a series is like an array that's used with Pandas, and the data frame is what's like a table. So with a data frame, what the syntax is doing is it's setting up a table of values that have these as the column headers, A, B, C, D, E, F, which are printed out here. Indexing kind of automatically happens from 0 and increments numerically. And then Pandas data frames don't have to include all of the same data type. So if I assign a simple numerical value to a column, it looks at how many rows there are, but just puts that, in this case, a float number into all of the rows for that particular column. So this is a float. Pandas has another format called a timestamp where you can put in dates. This is putting in the Pandas series into one of the columns because a series is just a one-dimensional array of data. So here I'm putting in the series, which have values 1. If you don't know Python, you don't have to worry about the syntax. This puts in a NumPy array. NP is what's for NumPy. And then Pandas also has a categorical data type. So categorical is important when you're doing machine learning, and you have to worry about identifying strings like this with categorical values. So in this case, it's test and train. And then in this column, I have a string. So if you don't understand the syntax, that's okay. But the basic idea to understand is that a series is like an array of values that's a Pandas specific data object. And the data frame is like a table. And then in the data frame, you have columns and you have rows. So let me just jump ahead a little bit here. Pandas, Pandas has a function called that you can call on the data frame. You can get the values of the columns by simply putting down the name. In this case, we've assigned the data frame to this variable df for data frame. Data frame has some attributes to it and some functions that you can call on it. So this period is our way of calling something on the object. df.columns will return the names of the columns. If you want to look at the index, df.index will return the index. So here it's a simple numerical index. It goes from 0 to 3. And what it's returning here, it tells you the data type. And it tells you what the type of this particular object is, which is an index here and an integer index here. But the basic information is included in between the brackets, which are the names of the columns and the names of the indices. You can also get the data types of the information that's included in the table. So df.dtypes will return the data types for all of the columns that are in your table. In this case, it's returning a pandas series. So pandas series, again, are like arrays. They have an index here, it's A through F. And for each of these columns, it tells you what the data type is. So for column A, this is a float. It's like a real number. There's the pandas data time for column B. There's a float for column C, integer, category, and then object for F. So you can get information about the data that's stored in your table by calling these, by putting the name of the data frame with a period, and then these particular strings to get the information out of them. So let me come back up here to the beginning. Well, not all the way to the beginning, but to the point where we imported pandas. When we imported pandas, so actually, in the interest of time, I think I'm just going to switch over to this one, which is finished. This will spare us kind of the time of having to type in everything. So when I come back here, just to remind you, in the finished notebook, we put the data from our Excel spreadsheet into this variable called wblist. wblist in between brackets with a 0 gave us the first row. wblist with 1 colon and then nothing for the ending gave us the rest of the data that's in the list. So in order to work with this in pandas, we have to convert that list into a pandas data frame. Pandas, in order to make a data frame, you call, the name of the library here is, we've aliased it as PD, and then dot allows us to call the function that's inside of this package. Data frame is the name of a function which will create a data frame for us. And then into this function, we pass in a parameter, which is the data values. So the data values are everything in wblist from element 1 to the end, and then the column names are simply the first row of what's in wblist. When we execute this, it prints out the result of calling that function. So here you can see is something similar to what I was showing you before with the table. So into the table, we now have the column names are what we passed in from the first row. And the elements that are inside of the table are all of the data values that we had stored in this variable wblist. Here are the indices for the tables, here are the column names. Right now it's just printing out what the result of this function is, but we want to take this table and do other things with it. So we assign it a variable name for later use. This is the same function that was up here in this cell, in this one. And we assign it to a variable named irisdf. Something else that you can do with pandas, which I intended to give a preview of here, is that pandas can give us an idea of the distribution of data by plotting routines. So in order to make plots with pandas, you call various functions that are available in the library. So the way you step down through a hierarchy of function calls in Python is you include these dots. Pandas is the name of our library. And then if we do .plotting.scatter matrix, it will generate a scatter matrix from the data frame that we pass into it. In this case, we're generating a scatter matrix from what we just assigned for our iris data frame, iris df. And we don't want it to plot the headers. We don't want it to, I'm sorry, we don't want it to plot the species name. When we look at this, all that we want to generate the scatter matrix for is these 4 columns, the 4 columns of the measurements. This is our category of iris, and we don't need to plot that. So we can tell, if I just copy this out, iris, if you call a function on the data frame called drop, you can drop particular columns. And I pass in the name of the column and axis equals to 1, just tells it that I'm dropping columns and not rows. So this is the format now to pass in the array just of measurements, and fig size sets the size of the figure. So what's generated here is a scatter matrix where you're plotting, say, petal width against sepal length is plotted here. Petal width against sepal width is plotted here. And then histograms of the data are plotted along the verticals, rather than just a straight line for plotting one variable against itself. The ones that are bars are the histograms where the variable names match up. So sepal width and sepal width, there's no important information to be plotted from plotting a variable against itself. So it plots a histogram. This tells you that most of the sepal widths are here at a value of around 3. If you're keeping track of the data that we're looking at, there should be 4 columns here, not just 3. And it's kind of weird that all of the sepal widths here are kind of clustered around here with 1 all the way out here. So just by visualizing data here, we can already tell that there are some things that might need to be addressed in looking at the data. For example, why isn't petal length shown? That's a missing column, seemingly. And why are the sepal width values so clustered along one edge? So we'll come to these. So I've gotten now down to where I talk about pandas. This I talked about before. So I'm going to scroll down and introduce some more.
So you know what it is? It's the who's the person that puts up the event, but she is putting our personal emails on that event.
I'm sorry, there's somebody talking.
Yeah.
Thanks. So I'm going to introduce some more basic functionality of pandas, because I think it's important to understand how pandas is working. Yo will be talking about this in his notebook tomorrow as well. So it's this is some fundamental and important information to know. Iris df is the name of our data frame. If we call the name of the data frame .shape, it gives us the size of the table. So 150 gives us the name of the rows, and 5 gives us the name of the column. So it has 5 columns because we have the species and the 4 measurements, and then 150 rows. So there are 50 measurements for each of the species. And if you want to know more particular information about the data types and column names, it's also useful to call the info function on a data frame. So irisdf.info, when you call it like this, will this returns what type of object it is. So it's a pandas data frame object. It tells you there are 150 entries. There are 5 columns. And then it tells you it tells you the name of the column, the numerical index of the column, whether the column has null values, and what the data type is. So this already starts to tell us some things which are funny about the, this tells us some things that we need to address about the data. One is that petal length is considered to be an object, not a float. Another is that sepal length has 100 non-null columns, rows, whereas all the rest have 150. So there are things to explore about this, the particular data that we've imported, which are evident here when we get information about the data frame. So there are some questions. Does object mean category? No, there's a different categorical data type, which we might come to in just a little bit later. But object in the Python sense is different from category. Shape does not include the header. That was another file, another question. So here you see when I list a particular column, maybe I didn't go over this particular one. This here is just printing the data frame, irisdf. If I just type the name of the data frame and hit shift and return, it will print out the information that's in the data frame. So here the data frame goes from 0 to 149, which is, it tells you here, it's 150 rows by 5 columns. So the column headers are not included when you come down here and look at shape. So we kind of know beforehand that it should be 150 rows because there are 50 measurements for each of those 3 species. We can look at a particular column by putting down the name of the data frame and then the name of the column in between brackets. So this is returning the species column in the iris data frame. If there are too many for it to print out, you can specify how many will be the default output. In this case, it's only printing out 10 values. And past 10, it will give you these 3 dots, which just tell you that there's more data in between, on different rows between these. Let's see, so that addresses some of the questions, I think. So another useful one to do is to come down here and say describe. So the name of the data frame with describe as the function, it has parentheses here without any parameters just to tell it this thing here, describe, is a function. So a function has to have parentheses after it. But if you don't want to specify any parameters that for the function call, you just leave this empty. And it calls it either with no parameters or just what the default parameters are for this particular function. When I execute this cell, it doesn't give me general information about the data frame. It gives me numerical summary about the data that's actually in the table. Isn't describe a method, not a function? Yes, I think so. Nice. So the count tells us the actual non-null values that are in the column. This again tells us that there's only 100 non-null values in sepal length versus petal width and sepal width. You might notice it doesn't give us a numerical description of the petal length column. And that's because it doesn't consider petal length to be a numerical column. It considers it to be an object column. And it doesn't give us a numerical summary about the species column. So as I mentioned, Pandas data frames can have, not all the elements have to have the same data type. That's kind of one of the differences between Pandas data frames and NumPy arrays. NumPy arrays all have to have the same data type. Pandas data frames can have a whole variety of different values inside of the columns. But getting back to this, it gives us the basic statistical information about the numerical values in the columns. If there are any nans, which are missing values or considered null values, it doesn't include them in the numerical summary. It only gives you the numerical summary about the non-null values. But here it gives us the mean, standard deviation, min and max, and the quartiles. Another handy one is to transpose the table. If for any reason you find that you've imported the data in this kind of flip side where you want the columns to be the rows and the rows to be the columns, you can call .t on the data frame and it will transpose the data frame for you. So here now, this considers the columns to be the numerical values which you had before, and the header values are now the row indices. But here this doesn't modify what the original data frame is. It only prints out what the result of this would be. So we haven't actually changed the underlying data frame that we're looking at. Head and tail are another good one. So head will tell you the first, say, several rows of the data frame. By default, it's the first 5 rows. Often you might be dealing with data frames which have many more columns than you want to look at. So head and tail are a way just to look at what's at the top of the data frame or in the first couple rows. Tail tells you what's in the last couple rows. And then this shows you passing a parameter. So in this case, if I include 3 in between the parentheses, it will only return 3 rows from the tail of the data frame, the last 3 rows, versus returning 5. So for the person who is asking questions in the chat, I think it might be better to ask that at the end. I can definitely answer those, but it might involve a little more time than just describing here. So coming back to this, another thing you might want to do when you're looking at the data, when you're trying to get an idea of what the data is showing you, is to sort the data so that the values that you print out are kind of at the limits of, at the numerical limits of whatever it is that you're looking at. So sort index is a way to sort the index of the data frame. In this case, I'm sorting axis equal to 1 means the columns, ascending equals false means that it sorts them in descending order. And by sorting the index, all I'm doing is in this case, I'm sorting strings. So it goes by reverse numerical order. So species is kind of the last in numerical order for the column titles. And petal length is the first. This allows you to sort by the columns. If you want to sort the interior values, you can sort values. So sort values, you have to pass the by parameter. In this case, it will sort them by sepal width. So sepal width, it automatically goes in ascending order. So it starts at the very lowest one and goes up to the top. You can see here now, it includes the entire row when it sorts by a particular value in the column. So these have been sorted in correspondence with whatever sepal width they're affiliated with. Doing something like this is a convenient way for us to look at some of the outliers. So when we were plotting back up here, we noticed that sepal width was all tended to be along one edge at the low values, and there was one, or it looks like there's one way up here. So by sorting by the values here, by sorting by the values, we see that particular value here at the tail. And we see the other parameters that are associated with it. We see the particular value that has, and the species it's connected with. So in this case, it looks like whoever entered the data simply was off by a factor of 10. They entered an extra 0 because something like 3 would be a more reasonable value than 30. For the question, is it better to have a nan or null values? In essence, they're considered the same. So they're dealt with the same way. We'll come in a little bit to how to deal with nans and nulls. And we'll come back to the steeple width is equal to 30 as well. So you can see we're starting to get a better sense of how it is that we want to modify values in this table. Here's a nan. We have to figure out how to deal with nans. There are a couple different ways. We have to figure out how to deal with outliers, and we have to deal with the fact that, you know, in this particular case, this column wasn't being identified as numerical when it should be. I'm going to talk a little bit now about how to access particular values inside of this. So if you have a data frame, you might want to pull out specific values, say by row index and by column index. The way you do that is with these 4 items: loc, iloc, at, and iat. Loc, so here I'll first print out an entire column. This prints out the steeple width column, or at least 10 elements of it, the first 5 and the last 5. This is where we have the value of 30 that we think we want to change. When I pass an index now to a data frame, the numerical index like this will consider this to be the numerical index for the rows. So this passes back to me the first 3 rows of the data frame and all 5 of the columns. I can start to get a little more specific with these additional methods. So the loc1 will pass me back the first row. So if something is passed in here, it's considered to be a row. If you pass in 2 items, let me write in something different here too. If I put the name of the data frame .loc and then say 1, 1. Oops. In this case, it gave me an error with 1, 1 because loc deals with the column name rather than the numerical index. So I have to pass in the column a string that identifies the column rather than the numerical index. And when I pass this in, this gives me the first row, and the first row, the species that's identified with it, Setosa. If I pass in a list, it will give me multiple rows. So the advantage of loc and the advantage of the at are that you can pass in multiple elements when you're trying to index, or when you're trying to access elements of the array. You can pass in, say, an array of elements, and it will give you back more than one item from the data frame. With iloc and iat, this is more, I'm sorry, with loc and iloc, you pass in the arrays. With at and iat, you only get one specific element with the at. So here to loc, I'm passing in a list for the columns. I pass in 2 column names in the list, and it returns to me the first row and these 2 columns inside of the data frame. And then I can also pass in an array, or multiple values. Say for the first one, this will pass to me the array of rows between 0 and 2, 0 first and second, and this petal length and petal width columns. All right, so that's loc. If you call loc and you call at with only 1 row and 1 column name, they will return to you the same value because they're referencing the same thing in the data frame. So these have the same effect, but you can't call at with something like this where you have, say a splice list, or you have something which is a list of values for the columns. So here, iloc1 will pass in just one particular row. So I'm only identifying it with one value for the parameter in between the brackets. And if I have one value for the row and one value for the column, that also counts as something that you can pass in with to iloc rather than to loc without the I. So these two are just more examples. So now I'm going to talk about a different way to get an index, to do indexing on the data frame. Let me actually consider what, yes, okay. So I'll mention this briefly. I think that there are some other things that I should be moving on to in the interest of time, but this will be helpful in particular for when we get to Yo's project tomorrow, and for some of the things that I'll be doing with the plotting. So hang in there. We're almost through the basics. Another way that you can index the data frames is you can pass in an array of true, false values. So this particular command that I'm looking at here, this looks at the data column for sepal width. And to that entire column, I apply, I look at the conditional greater than 10. What that returns to me is a series. And the series, for each element that's inside of this particular column, it evaluates whether that particular value in the table is greater than 10 or not. And it returns to me an array of values which are false or true depending on the condition. This is useful when you're looking at the table, because when I look at the table, let's say, there are a lot of rows in here that I'm not seeing inside of this data frame. And there are potentially a lot of other values that I'm not catching. I see this one, 30. So I've sorted it, which is convenient for telling me where this 30 is and the fact that there's only likely one here. But say that I really want to look at the entire column. And I want to look at the entire column, but only print those values which are outside of a certain range. If I want to search through a data frame like that with some kind of conditional statement, you can put the conditional statement inside of an index that you call on the data frame. So here, what I'm doing is I'm indexing the iris data frame with this particular condition. And this condition, which is an array of true and false, or it's a series, in this case, it's a series of true and false. It will only access iris.df and print the results when this is true, and it won't print them when it's false. So when I print this, it only returns that part of the data frame which satisfies this particular condition. So it's returning the row which has the abnormally large sepal width. So when I look back at this plotted data, sepal width here, this one outlier point is just 1 point. It's that 1 point that's 30, and it's that part which is kind of heavily skewing the data when we look at the distribution. So we want to find some way to deal with that. You might think, well, I can take this row that's returned and set it equal to 3. Really, we don't want to do that, because when you do that, it sets everything in that row to 3. If we look for the rows now that have the condition greater than 10, it has changed that 30 to a 3. But it's actually changed, if we look at the first row, which is where that particular value occurred, all of the values in that row have been set to 3. But you can get a sense for how it is that we assign new values to only particular rows which satisfy this condition. These are the values that row should have had, with the exception of 30. So with iloc, I access the first row, and to that particular row, I assign to it this list of values that resets the first row to what the values initially were for the species and the 4 measurements. What I really want to do is I want to satisfy the row that has this condition. So I use loc. The first parameter is the row, which is identified by this condition with true, false values. And then I only want to change that column, which is the second item here. I only want to change the column for the steeple width to 3. So when I execute that, now the first row has all of the right values in the other columns, but the 30 has been changed to 3. And when I try and plot the scatter matrix again, now we see a much nicer array distribution of the steeple widths, because we don't have the outlier here at 30. There's still something else that's not satisfactory about this, the fact that we only have 3 rows and 3 columns. So the petal length we noticed was problematic before because it wasn't considered to be numerical. You can get all of the unique values for a particular series or data frame by using this unique. So here we look at the series. This is the column values of the iris data frame for petal length. When we call unique, it doesn't list all of the values, it just lists the unique ones. In this case, you know, that all of the values might, for the most part, be unique. But it does allow us to identify something that's not numerical in this. It allows us to identify that there's an X, there's a string in the values. So here again, we can use our conditional. We want to know when the values for this particular column, when they're equal in equals in Python is this double equal sign, when it's equal to this string. This would return us all of the rows of the data frame, but there's only one particular one where X is passed into the petal length. We can also use at. At can be used for a specific row and a specific column. In this case, since we printed out the data frame with this particular condition, we know it's in the 37th row, or the row with index 37. We can look at the petal length column. That gives us our problematic value. And then we can assign a value to that that's different than X. So just say from consulting back at Fisher's paper, we know that rather than X, it has to be 1.4, a value of 1.4. So we're going to index the data frame at a particular row that satisfies this condition, where petal length is equal to X. And we look at the petal length column. And to this particular location where this is satisfied, we assign a new value 1.4. So if we look at that row again, now it has a value of 1.4 rather than X. And we can try and generate our density, our scatter matrix again. But that didn't help things. It still looks the same. So something's still not right. So let's look at the data types. If you know that there's a data type that doesn't satisfy how you want to represent the data, you can explicitly cast the column as a different data type by using the as type. So in this case, we know we want petal length to be a numerical column. We want it to be treated like a float rather than treated like an object. So if we, to this particular column, we use the as type, and in between the parentheses, we specify that we want this to be a float. And then we look at the data types again. The data types haven't changed because all that we've done here is we've called a function which prints out the values. It doesn't actually change the underlying representation of the data frame in memory. So one thing that this points out is when you're interacting with Pandas, when you're interacting with it for the first time, there might be some confusion that you encounter as to what modifies the underlying data structure and what doesn't. In this case, the function just returns, the function actually returns what we want. This output is printing out the return value of calling this. So what's returned has the data type of float64, but it doesn't modify the underlying column that's in the data frame. So sometimes in cases like this, you'll see what you really want to do is you want to assign what's returned from this to the data frame. In some cases, you can also do this in place, where the function modifies things in place rather than assigning it back. But in this particular one, I'm just going to say to the initial data frame, I want to assign the result of this, of changing the type for the petal length column to float. And in this case, the data types have been changed to float. Now, when I look at the scatter matrix, now I do see all four columns. So the scatter matrix itself is only operating on the in this case, the float columns that are in the data frame. For example, it doesn't also return a fifth column, which has the species. It only returns the something by something grid for the numerical values. But the important thing is now, when we converted petal length to float, now we can see the petal length distributions here as well. And one reason that this is important is because there's a feature here that Fisher noticed in his analysis, which is that one particular species, which happens to be this collection of points, is clearly separable from the other two species, which are included among these points. Coming back to the nans and the null values. Here we can call this method is NA to identify which values are considered nans inside of the data frame. In this case, the data frame is too big for us to see all of the values, but we do see here, if we were to look before at the nans that occurred, these would be where the nans are. So you can use this is NA to get an idea where the nans are. Is null will have a similar effect. So is null will also return true and false depending on where null values are. In this particular one, I'm going to use remember, info gives us general information about the entire data frame. In this particular case, the only part of the data frame that I want to look at is where these values are true here and not where they're false. So when I index this particular array, I pass in this conditional, this table of true and false values, and it only returns that part of the data frame for which this is true. So as you can see, none of the sepal lengths satisfy that. All of the sepal lengths are null, and there are 50 non-null values for the other columns. And I can, the other thing I can do is I can look at a particular species. So this is indexing the data frame when the species is equal to Virginica. In this case, Virginica is one of the species. And when I do this, I see that there are no non-null values for sepal length. When I come up here, let me find where the iris data frame is shown. Here, for example. This was the first data frame that we looked at. Here is where the nans are. And so nans for Virginica, there's also versicolor in here, and there's setosa. And there are 4 different columns that we're looking at. Looking at the info, when we make conditions like this, we've identified that all of the nans appear to be in the sepal length column, and all of the nans appear to be for the Virginica. So we've identified the particular nans that we want to change. There are a variety of different ways to handle nans. In this particular case, we're leaving out an important part of the data because all of the measurements for one particular genus are missing. If only one was missing, you might fill it in with an average. You might choose to drop the missing values. There are a variety of ways which you can deal with nans, but they're usually informed by how you want to analyze the particular data that you're looking at. So that's what I'll mention for nans at the moment. We come now to calculating values on a particular column. So say I want to get the entire number of values that are in the sepal length column. This is how I access the sepal length column of the data frame. And when I do .count parentheses, it gives me the count. You can see it's not 150. Whereas if I look at the entire count for iris data frame, this returns the count for all of the columns. All of them except for sepal length are 150. And that's because sepal length has null values for all of the Virginica species. I can also look at the mean. I can look at the mean for the sepal length column. Despite the fact that it has null values, it does return a mean. And it returns a mean for all of those that are non-null values. The other important thing, if you're familiar at all with SQL, you can do something similar with this group by. So group by is a way of calculating quantities split up between different groups. So say we want to look at the average values of sepal length, but not for the entire column. We want to look at it, the mean for each particular species. So you can use this group by species to tell it you only want to calculate this summary value on this particular column. And you want to split it up depending on the values that are in this column. So what that returns to you is for each species, for that part of the data frame where the species value is, say, Setosa. It looks at the rows where species is equal to Setosa, and it calculates the average of sepal length only for those rows. And then only for the rows where species is versicolor, and only for those which is species equal to Virginica. So if they're all nan, it returns a nan because there's nothing to calculate a mean on. You can do it for count as well. This splits up the count. This, if this was another, say, if it wasn't sepal length, if it did include numerical values, each of these should be 50 because there are 50 measurements for each variable, for each species. And you can group by multiple columns. So this returns the count where I've grouped both by species and by sepal length. So in this case, all I want to make sure is that the count for petal length, petal width, and sepal width are the same for each of the values of species and sepal length. And that tells me that there aren't any extraneous nan values in these other three columns. They should all be the same. If there were nans, one of these, say where the nan was, would be different from the count for other measurements. And if I look through these, all of the rows are the same. So we can relatively conclusively say sepal length is all null for Virginica and only for that species. Here's one way to change the values for the nans. You call fill NA and you pass in the value that you want to fill for it. So if I pass in 500, for each nan, it substitutes 500 for the nan. This is clearly not what we want to do. For this particular data set, we can go back to the published reference, fortunately, and these are all the sepal lengths that we want. This is a list of values. And so to bring everything back together, we want to, for those places in the data frame where that satisfy a row which has a species value of Virginica and a column value equal to sepal length, we want to replace those nans, or in this case, those values of 500 with the values that we passed in with this list. So when I execute that now, the values for Virginica are not nans, they're all replaced by the correct values. So I've gotten to the end of this first one, and we've kind of gone over our introduction to Pandas. So are there any outstanding questions? I know there's been a lot of chat on in the chat window.
Hey, Ben, maybe in the interest of time, you want to go to notebook 3 and just mention notebook 2?
Yeah, that sounds good. So there's this, let me close this. So I'm going to close and halt my other notebooks. There's a second notebook here, which you're welcome to go through the finished one. The basics of what that shows is that it's intended to demonstrate the different file formats that Python and that Pandas can work with. So it shows you how to import CSV files, which are comma-separated value files, how to import tab-separated value files, how to import JSON files, which are JavaScript object notation files, and then how to get data through the web. So you can access data through the web with the request library, as well as wget and curl, if you're familiar with those shell commands. So as far as getting data, if you want to explore different methods for getting data, this is a good notebook to check out. The one that we're going to go to now is 03, and I'll open up the one that's finished. So I think it's important to go over some of the different plotting routines that can be discussed here. For those of you who say that the binder service is down, occasionally it does require simply refreshing the browser page. So that's one suggestion, is just to try refreshing the browser page, and it might try and reestablish your environment. All right, so here's Notebook 3 introduces a variety of different plotting routines. All of the commands are already here, so I'm going to run all the cells beforehand just so that they're executed. But I'm going to come up to the top and show you what gets generated. So these first 3 cells are just importing the data again, importing them into a Pandas data frame. This is Pandas has a method called read_CSV, and to this method you can pass in the URL of a data source if you know one. So in this particular case, we're reading a CSV file into this variable, which is named the same as the first notebook, irisdf, and we're specifically setting the column values. So this is the data frame that we're going to be working with and plotting. That's already familiar. One of the most commonly used Python packages for plotting is Matplotlib. And it's intended to be a relatively comprehensive and somewhat low-level library for generating graphics. So its fundamental mantra is it makes easy things easy and hard things possible. It was originally built on the NumPy and SciPy frameworks to enable interactive MATLAB-like plotting inside of Python. So it gained early traction actually here in Pasadena at JPL and with the Space Telescope Institute. And it became one of the go-to libraries, open source libraries for academic publishing needs. The basic way that Matplotlib treats a graphic is you have a figure object, which is considered the entire space on which the graphic is generated. And then you have axes objects, which determine various features that are on top of the figure. And then at an even higher level, you have different elements that you can vary about the graphics, such as different markers, grids, and actual axis labels and tick marks, and everything that you want to customize about the plots. There is usually some type of Matplotlib function which will allow you to modify it. In this first cell, I simply import the functionality of the NumPy library, the Pandas library, and matplotlib.pyplot opens up the methods from this particular library for access. So whenever you see these 3 letters PLT, that refers to Matplotlib's pyplot here. The easiest way to generate a graphic is simply to PLT, you call plot, and then you pass in, say, the arrays of values that you want to plot. Simply calling this on its own will generate a plot. And if you only pass in one array, it just considers these the Y values, and it considers them to be indexed by the array index. So it goes from 0 up to 3, 0, 1, 2, 3. And then it assumes by default that you're going to be plotting a line plot. So this just plots a line between a linear line from 1 to 4. You can call different things on top of PLT and have them apply to the same graphic. So in this case, I'm generating the same plot, but I'm calling Y label, and that generates a label for the Y-axis. In this case, it assigns the string some numbers as a label for the Y-axis. A potential point in confusion when you're first interacting with Matplotlib is that PLT is offers the high-level functionality for generating plots, and the figure and axes objects enable you to modify the lower-level functionality that's inside of the graphic. So fig and ax, using fig and ax are another way to generate a graphic. When you call plt.subplots, this will generate the figure and axes objects. So this first line is just the way to instantiate the figure and axes objects. Ax, which is this axes object, also has a method called plot. And you call this just like you would call plt.plot. But now rather than plt, you're actually using the underlying axes object of the graphic. But essentially the functionality here is the same, where this list of values is being plotted, and the default is a line plot. And then ax has its own set of functions. This just sets the label for the x-axis to list index. It sets the y label to values, and it sets the title. If you pass in two different lists, now it will assume that this is for x, the horizontal axis values, and this array, this list, is for the y values. So it will still default to a line plot, but you can see the kinks here where these particular points are being connected together. So this is the quadratic. And now it's not being plotted from 0 to 3, it's being plotted from 1 to 4. You can further specify inside of this how you want the graphic for these particular points to be represented. So this is shortcut notation. When you pass in a string like this, the R tells you to plot red, and the 0 tells you to plot circles. So if you look up the documentation from Matplotlib, there are a variety of different symbols that you can include here to specify, say, whether you want circles plotted, squares, triangles, whether you want a dashed line, whether you want a different color here. This can all be specified rather simply in this string that's passed in after the x and y list of values. You can furthermore specify the limits to the axis. The first limits are for the horizontal, and the second are for the vertical. So we're starting to build up now the functionality of initially plotting the points, but then modifying the actual elements of the graphic. You can also call 3 different lists with the following strings in a row, and it will plot them as 3 different plots on top of each other. So here we're np.arange is just a way to generate a list between 0 and 5 spaced at intervals of 0.2. And then we plot t versus t, which is a linear plot. That's this bottom line plot. T versus t squared, which are the blue squares. And t versus t cubed, which are plotted as the green triangles. So this here is the notation for a triangle. So now we come to our iris data frame. say we want to plot the petal length versus the petal width, and we want petal length to be the horizontal axis, the petal width values to be the vertical, and we pass that into plt.plot. Well, this defaults not to a scatter plot, it defaults to a line plot, so it looks rather jagged. This isn't what we want. But there are other methods here that you can call besides just plot. We could pass in something like the R0. Here, there's another function called scatter. So scatter now would only generate 1 point per combination of these two lists. It's generating petal length on the horizontal axis and petal width on the vertical. So that's not immediately evident here because we haven't told Matplotlib that that's what we want to plot. But we can be a little more specific once we start adding additional commands to making the graphic. And we don't have to only plot one, we can call plt.scatter multiple times, and the plots will be generated on top of each other on this figure object. So here, this is the index to get that particular part of the data frame where the species is Setosa, or for the second versicolor, or for the third Virginica. And this is for the particular column we want to plot, petal width and petal length. And then we specify the figure size, which is 7:6. We specify a color for the points, and we specify labels, which here X is for the horizontal, Y is for the vertical. So it's always X by Y, yes. So I know we have hit the 11 o'clock point. I will continue just talking very briefly through this notebook so that you understand what it is that's being generated. But since we are at the 11 o'clock point, I'll stop here and ask if anybody has questions for those of you who have to sign off. By the way, I will probably also show this very briefly, just the main graphics from this notebook tomorrow morning so that you see some of the capabilities that are shown later. So to the question, why is Python more beneficial than a spreadsheet program like Excel? With Python, you can really bring the whole numerical analysis routines to bear on the data at hand. You know, in a kind of a more intuitively programmed manner than you might be able to do with Excel. You can also interact with data sets which are, say, hundreds of thousands of rows long and which you might have trouble dealing with in Excel. So one thing which I haven't really touched on is you can have Python interact with SQL and interact directly with databases. When you're really working with large amounts of data, it can be useful to abstract the numerical analysis and be able to splice the data in a very quick way like you can with Python. So interacting with it with the numerical analysis routines of a programming language can be very beneficial. As far as using Python versus R, that's a perpetual question, I think, which people are very happy to argue with each other about. Python, I think, tends to be the more predominantly used in the community, although usually when functionality pops up in Python, it gets subsumed into R in some way, and the functionality in R somehow gets written into functionality in Python, so that the two programming languages do in kind of an indirect way complement each other. R is very useful for statistical programming because it has such a large or a long history in statistical analysis. And Python kind of comes at things more from kind of a more traditional numerical programming sense. Okay, so I'm gonna work through things. I'll keep it relatively short, but just to march you through here. The numerical analysis that you can do on these, when generating these graphics, can get complex, and you can also, say, include loops and indexes to your data frames in the midst of generating the graphic. So here we initialize the graphic, here we subset the data, we iterate over the species, and we generate a scatter plot for each of the species. If you don't know Python, or if you don't want to sort through what this means, that's okay, don't worry about it. This is just a way to, with Matplotlib, to generate 3 different scatter plots and lay them on the top of each other and color each species with a different color. So this starts to, when we plot the data like this, we start to more easily see the difference in measured values between the different species. So Setosa is down in this corner, then versicolor, and then virginica up in the upper right. So if we want to try and classify the 3 species, depending on what the measured values are, this is definitely a good way to try and discriminate between the different species, and especially with the Setosa. The Setosa will be easy to classify. And this is simply another way to generate the graphic. Pandas has its own plotting routines. Pandas is built on top of, it uses the functionality of Matplotlib. Both Pandas and the Seaborn library that I'll be talking about later, you can generate graphics with Pandas and graphics with the Seaborn package, as well as calling additional commands which modify the plot as if you're using the Matplotlib package. This first loop simply assigns a color based on what the species name is. And then with Pandas, you simply put down the name of the data frame, and then you call plot with, say, a variety of different kinds of plots. In this case, this is calling a scatter plot. So this syntax starts to get a little bit easier than working with Matplotlib. All I've done here is call scatter on the data frame with an X and a Y. The X and Y, I simply specify what the column name is. I don't have to worry about indexing the data frame. And I also, you can see, I don't have to worry about specifying what the X and Y labels are. It automatically tries to do it. So Pandas offers, even above Matplotlib, another more high-level way of generating graphics. This is a scatter graphic. If I simply pass in this list of iris colors, which is generated here. So I'm still calling exactly the same scatter plot with an X and a Y, but then I pass in the extra C parameter with iris colors. It already generates, without having to do this more elaborate separation between different species. I can generate here a similar graphic where all the different points are colored differently depending on what the species name is. Someone had asked before about category types. Category is a specific type that you can assign to a column in a species. So if I explicitly call this simply with C is equal to species, it wouldn't know what to do because species is a string, it's not a numerical value, and it doesn't numerically automatically know how to deal with strings. So with strings and with categorical labels, it's a good idea first to convert them to a category type and then to explicitly convert it to something like a numerical value. So when you generate a graphic, it knows kind of a numerical order in which to assign the particular graphical value that you're trying to plot. So here now with scatter, I still call scatter with X and Y, but when I pass in the categorical codes to the seed parameter, now it can use the categorical code to assign a color, whereas before it wouldn't just be able to use the string values of species to assign a color. And with black and white, the white kind of falls off the grid here because that has a white background, but you can assign a different color map. This just uses rainbow to get a more visual representation. And then I mentioned this one before, scatter matrix. Scatter matrix now takes the name of the data frame that you want to plot. This is the category that it's going to color things by. This is the color map, and this is the size of the figure. So here now we're starting to get towards a prettier graphic with a little fewer lines of code than we would with Matplotlib. Matplotlib, we could still call underneath of this to modify additional elements of the graphic if we wanted to. But this allows us to get, you know, what's starting to be a nice little visual. This is showing applying Matplotlib to the to Pandas. This generates a histogram of petal width values. And then if you work through the code, this part here, this is calling the plot root method on the iris data frame. This is the Pandas part of thing. But everything that's outside of this is like Matplotlib. So I've generated the plot with Pandas, but then I've modified the underlying elements of the figure and axes objects, specifically with something that's Matplotlib. And those work very well together. So now I've combined both Pandas and Matplotlib. And then, you know, it doesn't take long before, if you want to make very nice graphics, you can quickly get much more complicated in the commands that you execute in order to generate the graphic and the specific parts of the graphic that you want to look at. Seaborn, I mentioned just a little bit easier. So Seaborn, if Matplotlib tries to make easy things easy and hard things possible, Seaborn tries to make a well-defined set of hard things easy too. So what Seaborn is particularly useful for is something like statistical graphics. When we're plotting the iris data frame, you know, Seaborn is built on top of Matplotlib and closely integrated with Pandas, so you can very quickly make statistical graphics with this. I'm importing Seaborn as SNS, that's the alias. So simply calling scatterplot and passing in the particular columns from the data frame that are petal length and petal width is enough to generate the scatterplot. And if we want to style it by the species, Seaborn much more clearly knows how to separate out categorical values from this, even if they're like strings. So here it's doing it by style. There's a circle, an X, and a square. If you pass in hue, it will do categories by color instead. So this is a very quick way now of looking at the iris data frame. Seaborn is very handy when you're doing quick statistical graphics. And for something like the scatter matrix, all we have to do is call pairplot and pass in the name of the data frame and how we want to color it. So species, we color it by the different species. And then it generates something which is like the scatter matrix that we had before with Matplotlib. It doesn't have the histogram, you know, of say sepal length here. It actually includes the histograms of the additional columns, which aren't sepal length, along the diagonal. And then, this is very nice to look at compared to what we were looking at with Pandas and Matplotlib before. We could come up with something like this with Matplotlib, although it would take much more work to get something that looks kind of snazzy like this. So Seaborn is very good at making these snazzy graphics a little easier to do and combining that with the Pandas data frames. There's a question, are fig.show and plot.show or plt.show exchangeable? I think so, yes, although I would actually have to consult the documentation on that. I'm not sure. But I think in the sense of Jupyter notebooks, they end up having the same effect. Another kind of thing to end with talking about Seaborn is, let me increase this size. Not only can you make scatter plots like these, you can make a scatter plot with a regression line on top of it. So you're able to make some summary statistics like this fairly easily with Seaborn. In this case, it's only passing in 2 parameters, the petal length and petal width, and it's generating the nice looking scatter plot and then plotting on the linear regression line along with the statistical deviance around the regression line. So Seaborn is definitely very handy for looking at statistical aspects of the data sets as stored in the Pandas data frame. So now we're starting to get into a little more interactive libraries. There's Plotly, which I'll talk about here, and then Altair is the last library that I'll be talking about. Plotly is an interactive open source browser-based graphing library, and it's built on top of JavaScript. So you can really create beautiful interactive web-based visualizations with Plotly, as well as saving them as standalone HTML files. So there's a very quick way to use it is to use not just the main library Plotly, but plotly.express. Plotly.express allows you to generate very quick graphics. Here I pass in the data frame and the X and Y values, and the color is colored by species. This is a very quick way, again, to get the scatter plot. And now, if you scroll on top of the different data points, you also note that it has a little hover box telling you the values. I can zoom in on particular ones. So this is the evidence of some of the JavaScript that the library is based off of. So this is very handy when you want to have an interactivity like this with the graphic to try and say identify certain points. You can include additional things about the hover data. You can include an additional variable besides color, like the size. And then you can even make 3D graphics. So this is Scatter 3D. And this now has not just the interactivity where you can hover on top of it, you can actually zoom in and out. I can rotate this. There are some very snazzy things that you can do with Plotly because it's based on this interactive graphics in JavaScript. And finally, with Altair, Altair is based on a different conceptual notion of interactive graphics. So if you're familiar with ggplot2 from R, Altair is kind of along a similar vein of that grammar of graphics. Altair is also meant to be very interactive. So with Altair, the way that you structure how you specify the plot that you want to make is a little bit different because you're specifying things by this grammar of graphics where you have different elements which build on top of each other. In this case, I don't simply call scatterplot. for the library, I say, first I declare a chart where I pass in the data frame. Then I specify that I want it to be, this is for like a scatter plot where it consists of points. And then I encode on top of that what it is that I want to be those points. So there's an X, a Y, and a color. So this is Altair's way of making this graphic. You can also make a bar plot. This simply makes a bar plot. So in contrast to mark point, I call mark bar. I'm going through this relatively quickly, but you can read a whole lot more about it on the Altair documentation pages. This passes in sepal length as X. You can pass in aggregate values for other axes. You can color them by the species. So the interesting, very neat feature about Altair is that you can combine different graphics together. So here I'm just plotting them in kind of vertically next to each other. So C in bars, I define C. C is this Altair chart. Bars is the bar plot chart. And then you can specify selection elements. So in this case, I'm going to specify a selection interval. I assign it to this particular variable. And then if you go back up and look at the plotting routines, this is the code up top that was generated the scatter plot. This is the code that generated the bar plot. And then on top of the scatter plot, I'm going to add the selection, this particular selection on top of it. And I'm going to transform the bar plot by this same selection element. And what that allows me to do now, when I highlight something on the graphic, it will only plot that part of the bar plot which corresponds to the particular selection that I've highlighted on the scatter plot. So in this way, you can start making graphics, and you can start making multiple side-by-side graphics where you look at a particular thing in one graphic and are able to visualize, say, other measurements or other plotted values from only that particular kind of data that you want to interact with on the other plot. So if I look at here, that just plots the histogram for these particular points. I can actually make the interval and then I can move it around. So this gets really super snazzy and kind of very fun to play with. You can also do it this this one resets the axes, and then for this one I do a similar thing just with different two different scatter plots. So the same above and the same below. And then to make things really kind of nice, you can save them. When you save the charts, this is the specification for the two charts here that are combined. And I call the save, and I pass in the name of the name of an HTML file. It's saved here, the HTML file. And the HTML file itself encodes this functionality inside of it. So now I have an HTML file which exists independently of the Python plotting that I've done. And I can come over here and I can vary the, I can interact with the data through this web page. So I think that officially gets us to the end here. Sorry we went a little over time, but I hope you all got a lot out of this.